Crude oil is a mixture of many types of molecules called hydrocarbons. There are thousands of them, and their boiling points are so close together it would be nearly impossible to separate them individually. But this is not necessary. Instead, crude oil is lumped into groups called boiling fractions. Each one covering a range of boiling points.
The gasoline that is distilled directly from crude oil, called straight-run gasoline, by itself is not high enough octane for the modern vehicle. When enough gasoline, turbine fuel, and diesel fuel have been distilled, a lot of heavy fuel oil is produced as well. By using another process, cracking, heavy oil can be converted into high-octane gasoline. Heavy oil is made up of molecules that can be represented like this. When heated to very high temperatures, their movements become violent. Eventually, they shake apart or crack. In cracking into smaller molecules, most of them change their shapes and take on new properties. Most important of these properties is a higher octane gasoline. This reshaping process depends on a substance called a catalyst. The catalyst is any substance that stimulates a chemical reaction without itself being affected by it. Hundreds of substances do this, some more complex, some more simple, like these pieces of copper. This demonstration shows how they work. These two liquids normally react very slowly when they are mixed together. Now we add the copper. The reaction is speeded up. When the action is complete, the catalyst is unchanged and can be used again. Many catalysts are used in a refinery. One of the most important uses is in a catalytic cracking unit, a cat cracker. The catalyst used here consists of silica and alumina in the form of a fine powder. To do its job effectively, each grain must present the largest area possible to the heavy oil that is to be cracked. The catalyst also has to circulate freely in the cat cracker, and to do this, it must be made to behave like a liquid. At rest, the powder is a solid mass and will support a metal object. But if gas or vapor is blown through, it is turned up or fluidized. Now the object will sink as if it was in a liquid. To do its work in the cat cracker, the catalyst must be heated to more than 1,000 degrees Fahrenheit. Then, at the base of the unit, hot catalyst and heavy oil meet, and the cracking begins. The heavy oil is immediately vaporized, and the vapor in turn fluidizes the catalyst. This mixture rises to the reactor. Here, the heat and the catalyst complete the cracking reaction. Before long, however, carbon forms on the catalyst, clogging the openings. This reduces the working area and makes the catalyst less effective, so it has to be cleaned. It's fed to a regenerator where the carbon is burned off. The burning also heats the catalyst back to its working temperature, and it's ready for use again. This is the cycle of the cat cracker. Steady flow of catalyst meets a steady flow of heavy oil, and cracking goes on continuously, producing new shapes of high-octane gasoline. Besides gasoline, cracking produces petroleum gases and diesel fuel. All these products are passed to a distillation column where they are separated. But cracking doesn't provide enough high-octane gasoline to meet the demand. So low-octane straight-run gasoline is converted to high-octane gasoline by catalytic reforming. Straight-run gasoline consists mainly of short, straight molecules. To upgrade these shapes, these molecules must be changed, that is, reformed. As before, heat and a catalyst are required. And again, high-octane gasoline is produced. The catalytic reformer uses platinum as a catalyst. A thin film of platinum is coated on pellets of aluminum oxide, and they are packed in the reactors. But reforming requires a lot of heat, and the process has to be done in 3 or more stages. The straight-run gasoline is heated to more than 900 degrees and fed into the first reactor as vapor. As it passes through the catalyst, reforming begins. But so much heat is absorbed by the reaction that it stops before reforming is complete. When it leaves the first reactor, the vapor is only partially reformed, so it must be reheated and sent to the second reactor. Again, the vapor cools below its proper reaction temperature, and the reaction stops. To reform the vapor completely, it must be reheated once more and fed to the third reactor. Here, any remaining straight-run gas molecules change into high-octane gasoline. During most of these reactions, a lot of hydrogen is released. Its presence not only inhibits the formation of carbon on the catalyst, it is also valuable for use elsewhere in the refinery. These then are the principal refining processes: crude distillation and vacuum distillation, which separate crude oil into various products. Cracking, which converts heavy oil into high-octane gasoline, and reforming, which converts straight-run gasoline into high-octane gasoline. This is only part of the story. Other processes turn out additional products, as well as providing many raw materials for the chemical industry.
The very long carbon chain liquids such as bitumen and paraffin wax are piped away to be broken down elsewhere. The hydrocarbon gases rise up inside the tower, passing through a series of horizontal trays and baffles called bubble caps. The temperature at each tray is controlled so as to be at the exact temperature that a particular hydrocarbon will condense into a liquid. The distillation process is based on this fact. Different hydrocarbons condense out of the gas cloud when the temperature drops below their specific boiling point. The higher the gas rises in the tower, the lower the temperature becomes. The precise details are different at every refinery and depend on the type of crude oil being distilled. But at around 260 degrees, diesel condenses out of the gas. At around 180 degrees, kerosene condenses out. Petrol or gasoline condenses out at around 110 degrees, while petroleum gas is drawn off at the top. The distilled liquid from each level contains a mixture of alkanes, alkenes, and aromatic hydrocarbons with similar properties, and requires further refinement and processing to select specific molecules. The quantities of the fractions initially produced in an oil refinery don't match up with what is needed by consumers. There is not much demand for the longer chain high molecular weight hydrocarbons, but a large demand for those of lower molecular weight, for example petrol. A process called cracking is used to produce more of the lower molecular weight hydrocarbons. This process breaks up the longer chains into smaller ones. There are many different industrial versions of cracking, but all rely on heating. When heated, the particles move much more quickly, and their rapid movement causes carbon-carbon bonds to break. The major forms of cracking are thermal cracking, catalytic or cat cracking, steam cracking, and hydrocracking. Because they differ in reaction conditions, the products of each type of cracking will vary. Most produce a mixture of saturated and unsaturated hydrocarbons. Thermal cracking is the simplest and oldest process. The mixture is heated to around 750 to 900 degrees Celsius at a pressure of 700 kilopascals. That is around 7 times atmospheric pressure. This process produces alkenes such as ethene and propene and leaves a heavy residue. The most effective process in creating lighter alkanes is called catalytic cracking. The long carbon bonds are broken by being heated to around 500 degrees Celsius in an oxygen-free environment in the presence of zeolite. This crystalline substance, made of aluminium, silicon, and oxygen, acts as a catalyst. A catalyst is a substance that speeds up a reaction or allows it to proceed at a lower temperature than would normally be required. During the process, the catalyst, usually in the form of a powder, is treated and reused over and over again. Catalytic cracking is the major source of hydrocarbons with 5 to 10 carbon atoms in the chain. The molecules most formed are the smaller alkanes used in petrol, such as propane, butane, pentane, hexane, heptane, and octane, the components of liquid petroleum gas. In hydrocracking, crude oil is heated at very high pressure, usually around 5,000 kilopascals, in the presence of hydrogen with a metallic catalyst such as platinum, nickel, or palladium. This process tends to produce saturated hydrocarbons such as shorter carbon chain alkanes, because it adds a hydrogen atom to alkenes and aromatic hydrocarbons. It is a major source of kerosene jet fuel, gasoline components, and LPG. In one method, thermal steam cracking, the hydrocarbon is diluted with steam and then briefly heated in a very hot furnace, around 850 degrees Celsius, without oxygen. The reaction is only allowed to take place very briefly. Light hydrocarbons break down to the lighter alkenes, including ethene, propene, and butene, which are useful for plastics manufacturing. Heavier hydrocarbons break down to some of these, but also give products rich in aromatic hydrocarbons and hydrocarbons suitable for inclusion in petrol or diesel. Higher cracking temperature favors the production of ethene and benzene. In the coking unit, bitumen is heated and broken down into petrol alkanes and diesel fuel, leaving behind coke, a fused combination of carbon and ash. Coke can be used as a smokeless fuel. Reforming involves the breaking of straight-chain alkanes into branched alkanes. The branched-chain alkanes in the 6 to 10 carbon atom range are preferred as car fuel. These alkanes vaporize easily in the engine's combustion chamber without forming droplets, and are less prone to premature ignition, which affects the engine's operation. Smaller hydrocarbons can also be treated to form longer carbon chain molecules in the refinery. This is done through the process of catalytic reforming. When heat is applied in the presence of a platinum catalyst, short carbon chain hydrocarbons combine to form aromatics used in making chemicals. A byproduct of the reaction is hydrogen gas, which can be used for hydrocracking. Hydrocarbons have an important function in modern society, as fuel, as solvents, and as the building blocks of plastics. Crude oil is distilled into its basic components. The longer carbon chain hydrocarbons may be cracked to become more valuable shorter chain hydrocarbons. And short chain molecules combine to form useful longer chain
Transformer
molecules.
oil in different stages of use. From the left to the right. Left is more or less new, and up to the darker colors is transformer oil which has been exposed to loading in transformers. Mineral oil. And I will show, this is what I got 2007. Mineral oil.
пропитанный, и он намного лучше держит воду. Он там не уплотняли, оно
Сейчас сливаем образцы очищенного топлива. Все.
Secondary stage filters. Most of those will be removed. Then the water goes to the vacuum separator. Water and the gas are separated from the oil by these devices. The gas will be removed by these devices, and the water will be cooled down by these devices. Cooled down by these devices and removed from here. The last step is the oil goes